Hi, in the previous tutorial I mapped out the software that would make the simple digital voltmeter work. And I didn't use the computer, I instead used paper. And we looked at what variables that we're going to use, we're going to need. We looked at some of the functions that we were going to use as well. In fact, even a function that we're going to have to create because it's not available in the Arduino system. And then finally I looked at the software in a step-by-step way. The initialization here, and then the actual software that runs in a loop over and over again, displaying each of the digits, reading the analog to digital converter, converting it into a voltage reading, and then outputting it to the display. So now let's write this in C on the computer. We'll go over to the computer and do that just now.
Okay, let's just jump right into writing the software here. So just referring to the paperwork I did, I'm going to start declaring variables here. So to declare a variable, you need to tell the compiler what type it is. And there are various types of variables. And if you go onto the Arduino website and click on the reference tab up here, this is what you'll get. And here are the different data types that Arduino supports. So I'm going to get 4 bytes here, or 4 storage locations for each digit. We know that each digit only goes from the range of 0 from the range from 0 to 9. And so we don't need anything very big to store that in. And the smallest storage that the microcontroller can do is a byte, and that's 8 bits. And that means it can store a range of numbers between 0 and 255. So these display digit holders are going to be a byte. That's all we need. So we have to, first of all, you declare the type when you declare a variable, and then you give it a name. Display digit, and this one's the first one, so display digit 0, and a semicolon. So pretty much almost every line of code that you write in C has to be followed by a semicolon. If you neglect to put one in there, the compiler will complain loudly and stop compiling. And often the error will not be on the line that you left the semicolon off of. It could be somewhere else. So let's just copy and paste this here. We need to get 4 of these all together for the display digits, and we got to give them all different names. Again, if you name these all the same, the compiler is going to complain. It doesn't like that, and so got to give them different names. So those are the display digits, and we now need to come up with a variable for storing the pointer to which digit you're going to be displaying. And we know that there's only 4 digits, so 1, 2, 3, 4 is the range of numbers. So again, we don't need anything bigger than a byte for that one. And this, we'll call it digit count. Let's offset this from the other ones. And now we need to get the raw analog value from the A to D converter. We've got to store that because we're going to be using it in a calculation, so we have to put it somewhere in the meantime. And we know that the A to D converter is a 10-bit converter. It's 2 bits bigger than 8 bits, so the value coming out of the A to D converter is bigger than a byte. And so we're going to use something that's called an int, and that's 2 bytes, and it can store numbers in the range of 0 to 65,535. And so we'll call this one vraw. And then the last variable that we talked about was the result of the calculation, from which we'll derive the digits that we're going to display. And when I did the calculations, I found that the number, when I finished the calculations, the number is going to be quite large, and it's even going to be bigger than 65,000. So it's got to be a variable that's bigger than an int. And the next one in line is the long. And we'll call this one v in, the semicolon there. As you're entering code, it's helpful to frequently save it in case the power goes out or something screws up and you lose your data. Another thing I want to mention here is comments. And when you have your code written the way it is right now, you may have to come back to it 6 months or a year down the road to use it again, or to copy it and modify it for some other project. You want to know what's going on in your software, so talk about what's going on. Tell yourself, especially, because you're the one that's probably going to have to go back into it, but also tell everybody else what's going on. So I usually start my file with a just a description of what the software is going to be doing. And to put in a comment, you have to indicate to the compiler that what's the text that you're writing is actually a comment, so the compiler just ignores it. So if you're going to type some paragraphs, which you should do at the beginning of the program, just describing how the program works, you wrap your comments in these two symbols, / and a star. And you notice how everything now got grayed out. That means it's a comment. And you end the comment stream with * /. So that means everything in between here is going to be blank or ignored by the compiler. That's the multi-line comments. If you've got just single line comments, you can use a // and then everything that you write after that // to the end of the line is considered a comment, and the compiler won't do anything with it, just ignore it. So we could say storage for the digits to be displayed. And then down here, let's put a comment in points to the currently displayed digit. And down here, vraw, raw, and analog to digit converter value. And then we could call this one, say, the calculated. There. So I encourage you to use lots of comments, because I think down the road you're going to find that you're going to need them. I know I've done it so many times where I've written some software, hacked it out real quick and fast, got it going, forgot about it, and then remembered it 6 months later that I could use a piece of that software to do something else, and I go back and I look at it and I've got no comments, and I go, I can't figure out what I've done here. So I started doing lots of comments. And often before I write something, I will make the comments first, and that helps me think a bit more about the software and to write it more correctly. So that's another method you could use. Now we've done our variables that we talked about. We're going to need some functions, and there's two functions that I talked about that have to be always implemented in your software, and one of them is called setup and the other one is called loop. Inside the function setup, that you fill in the blanks, you fill in the instructions inside setup. Whatever's inside setup will get run once every time the microcontroller is reset or powered up. And same with loop. Whatever code that you put inside of loop gets executed repeatedly after setup has been executed. So let's implement these two now. To implement a function, you have to declare the return type, and some functions merely just do something. You don't need to input any data into the function, and when it's finished it doesn't return a value. For example, you could have a function that adds two numbers together. The inputs would be the two numbers you want to add, and the return value could be the result of the addition. But in this case, setup doesn't return anything. In fact, setup just does something. It doesn't really act on any variables. So to declare a non-return value, you use the word void. And then setup is the name of the function. And then you follow it by brackets. And inside these brackets would go the parameters that you wanted to pass into the function to be used. And I'll describe how to do that in another function that we have to write. In this case, there's no parameters, so we write void again. Although I think in C++ that void is unnecessary. You don't have to write it. Now, to offset the instructions that are just associated with setup, you need to use curly brackets. And so I put one at the very end, an open curly brackets, and one at the end of the function. So what that means is anything that you write in between these two curly brackets is what is associated with this function setup. So that's setup. We'll write something in there in a minute. Let's just we'll do loop as well. And you notice that I didn't put a semicolon after the end of this one. It's not necessary. This is one of the few places that you don't need a semicolon. The next function is loop. Again, it's like setup. It doesn't take any variables and it doesn't return any. So we write void loop, and in the brackets void, and then the opening and closing curly brackets as well. And that's it for those two functions. I'll save it. Now there seems to be something wrong with setup. I think what it is this: it doesn't like the capital U. Setup should be highlighted like this one, and it's not. So maybe I've just mistyped it. There we go. That's what it looks like. So in setup, if we look at our paperwork again, and we look at what we decided we need to do inside setup, I've got written here initialize the I/O pins and initialize variables. So we want to be able to set up the I/O pins that we're going to use. Now, looking back at the schematic, I have connected all of the segment drivers to pins 0 through 7. And when the microcontroller starts up from power up or from a reset, all of the I/O pins automatically come up as inputs, and we need to make them outputs. So the function to make an I/O pin an output or an input is called Pinmode, and it's already declared for us, so I don't have to set it up like I just did with setup and void. So what I'm going to do is everything that's inside the curly brackets of setup, I'm going to indent it by 2. And that way it offsets it from everything else and it makes it easier to read. So the function is called Pinmode, and it takes 2 variables on the input. The first one is the pin number that you want to work on, so we'll start with 0. And then a word that defines what state the pin should be, either an input or an output. And in this case, we're going to make it an output, so I just write output, all in capital letters. It has to be in capital letters. Now this has to be followed by a semicolon as well. So now we've just set up pin 0 only as an output. I want to do all of the pins that way. So I'm just going to do some more cutting and pasting, and we'll have to do a bit of editing. So we want 7 more. So 1, 2, 3, 4, 5, 6, 7. So now we have to change which pins we're going to work on as 1, 2, 3, 4, 5, oops, I put 2 4s there, 5, come on, 6, and 7. So that's our segment drivers are pins 0 through 6, and our decimal point is on pin 7. Now I want to make the I want to set the state of those pins in order to turn off the display. So to turn off a segment, you simply make the that pin high. So we'll use another function called digital write, and it takes 2 parameters as well. It takes a pin number, again pin 0 we'll start with, and what state we want it to be in. You want it high or we want it low. In our case we want it high. Again, it has to be a capital letter, because actually these words, output and high, are defined somewhere else in the Arduino system to have a certain value, a number, and the compiler looks at that and knows that. And also, I didn't mention it, but the parameters inside here are separated by a comma. If you had a function can take many variables, so every variable that you have in there just gets separated by another colon, another comma. So variable A, comma, variable B, comma, variable C, etc., etc. So that's how you give the parameters that you need, that function needs. If you have to be careful of what parameters you give it. The parameter that you give it has to match the type that the function was declared with. So you can't, let's see, let's go back a bit here. I can put in not only a number or a defined word, I can also put in a variable. So for example, I could put digit count in here, and what the compiler will do is look at the value of digit count and put it into the parameter into this parameter. But if I had declared this parameter to be an int instead of a byte, and I tried to put digit count in there, the compiler would complain because it's not the same type. That's probably some information for another tutorial. But also, if you go to the Arduino's reference, and I believe if you dig around in here, you will find some instructions on how to declare your own variables. So let's go back to the software here and continue on. So we want to make all of these pins high, so I will just copy and cut and paste again. And 1, 2, 3, 4, 5, 6, 7. So again, oops, that'll be 0, this will be 1, 2, etc., etc., all the way down to pin number 7. There. So now I've dealt with all of the pins that are driving the segments of the 7-segment displays. Now I need to deal with the pins that are connected to the digit drivers, the ones that turn on each of the digits. And I hooked those up to pin numbers 8, 9, 10, and 11. So essentially I've got to do all this again for those pins. So I'm just going to cut and paste, copy those ones, and I'll put them down here. And we'll put in 8, 9, 10, and 11. And also I need to make them high as well in order to turn off the displays. Probably doesn't really matter. Either one of either side, either the segment driver or the digit driver high would turn off that particular display. But I'm going to do it for completeness here. So I'll do another cut and paste. And I'll put in 8, 9, and 10, and 11. There. So now that is our initialization of the I/O pins. Now you should get into the habit also of initializing your variables. What happens in the C compiler is it does initialize your variables for you. but it initializes them all to 0. It generates a piece of software that knows all about all of these variables, and it runs when you first power up. You don't see it happening. It's all done in the background, but it's done automatically for you, and it just makes all of these variables equal to 0. But what we could do is, if we wanted to, we could make them any value that we want. And the one way to do that is in the setup function here. So I'm just going to do some more cutting and pasting here and put those in there. We don't need byte anymore because we're not declaring it, we're just doing the digit itself. And then we put in an equal sign and the value we want it initialized to. So I'm going to call it 0. And I want to point out here, the equal sign does not mean equals to. It's an operator, and it's what's called the assignment operator. So what it means is digit 0 is assigned the value of 0. That's all the equal sign means. If something is equals to something else, then you need two equal signs, and I'll explain how that's used in a bit here because we're going to use it in the code. So let's get rid of the byte for this one. We'll make this one assign the value of 0, and we'll go on and do the other ones as well. And you notice I've spaced these out. I put spaces in here that offsets the assignment operator here. It just looks better. I've done the same here, separated these with a space. It makes it easier for you to read. The compiler doesn't care. And another thing, so just think about spacing things out everywhere. It just makes things look better. You don't have to worry about spaces anywhere. And also, you noticed how I've put all of these instructions on a single line. But again, the compiler doesn't care. You could have them all on one line like this, and it would work just as well. The compiler is going to compile the same code the same way. It's not going to complain. But it makes it a lot harder to read. So I encourage you to offset everything like this in chunks, and it just makes it a lot easier to read. White space is really important in writing software as much as the instructions itself. So display digits have all been initialized, and then let's go and do digit count. Actually, we'll just do this and put it in here. And vraw, it doesn't really matter what these values, what these are going to be initialized to, because they're going to get used right away anyways. Sometimes is when you use them expecting them to be a certain value and they're not, and you end up with some weird results in your code. That doesn't happen very often, but it's something to keep an eye out. Alright, done. So we've written our setup routine. This is routine runs once right after power up. Now loop. That's going to take a little bit here, some structuring. So looking back at our paperwork here and what we had written here, we need to read the analog pin. So the function that we use for that is called AnalogRead. And so VIN is, no, actually VRAW is the variable that we're going to put that data into, equal, or as assigned the value of AnalogRead. And the parameter that we have to put into AnalogRead is the pin number that we're reading from. And in this case, it's a 0. Close brackets and semicolon. Before I go too much further, we should probably throw in a few more comments here just to make things easier to read. So single line, set up the I/O pins for the segment drivers. And then down here, set up the I/O pins for the digit drivers. And we could, I mean, it's pretty obvious, but initialize. Is that right? Yeah. And let's go back. Oh, I did that already. Comments were there. Okay, let's go back to the loop now. So we read the analog input, and we've got to do some calculations with it. So vin is assigned the value of, and vraw times, that's a star, that's the time symbol, we don't use an X here, our constant that we calculated in a couple of tutorials ago, 1465. Then we're going to subtract 500 to give us the rounding, and then we're going to divide everything by 1000. Now there's an order of precedence in these calculations here, and what's going to happen the way I've written it here is vraw is going to get multiplied by 1465, 500 is going to get divided by 1000, and then the subtraction will be done. So we can't have that because it will give us the wrong answer, but we can use brackets, parentheses, to make it work. So we put a parentheses around this. So what will happen here is the vraw will get multiplied by 1465, then 500 is subtracted from it, then the whole mess is divided by 1000, and then of course our semicolon. So that's the vin calculation. That's not offset quite right. Let's see what happened here. Okay, it's the other one that's not offset. Oops. There. All right. So that is the calculation for vin. Now the next thing is we're going to work with the 3 or 4 digits. We have to convert each. We have to do some more calculations to convert vn into each of the individual digits. So the first digit we'll work on is the left-hand digit, the most significant digit, which would be the tens of volts. So what did I call it? Display digit. Display digit 3 is assigned the value of. Now we're going to take vn and we're going to divide it by 1000 again. So remember in our calculations, when we did all of this calculation here, we came up with a number that's between 0 and 1500. So when we divide 1500 by 1000, we get 1. So that's going to go into the first digit. Now let's look at the next one. Digit 2. Now we're going to do a different kind of a division here. So we're going to take vn again. We're going to divide it again by 1000, but we're going to throw away the answer and just keep the remainder. And there's a function that, or an operator that we use. It's called div, and it's written by the % sign. So I'm going to div by 1000. And then what's left is you take away the left-hand most out of, if it's 1500 for example, you div by 1000, you're left with 500. So I want to get the 5 out of there, so I divide this time by 100. And that gives me 5 for display digit 2. Then we'll work on the next one. Again, vn. We want the remainder again. by 1,000. This time we want the remainder of the remainder by 100. And then we'll divide that by 10. And that'll give us the next digit. And finally, display zero. Again, we'll do all the diving, v-in, divided by div 1000, 1000, div 100, div 10, 10, and that's the end of it. That gives us our last digit. So that's how we compute our different digits here. So we can put in a few more comments. Read the analog and then we'll convert. So get convert to volt. And then fill in the digits. Okay. That's that part. Now let's display these digits. Now we'll start with the right-handmost one because that's the way I started scanning it. So that's digit 0. So we've got a counter, digit count, which we have up here, and initialized to 0. And what digit count's going to do is go 1, 0, 1, 2, 3, and then back to 0 again. That's 4 counts. So that points to each of the 4 digits. So let's just look at digit count. And if digit count is equal to 0, that means it's the first digit, the right-handmost digit, digit 0 that we're going to work with. So let's do that. So we'll type the if statement. If digit count is equal to, now there's where the 2 equal signs come from. We have to differentiate between the assignment operator and the equals to, and that's what we do here with the 2 equal sign. So if digit count is equal to 0, if that's true, then we'll execute what's in these brackets here. If it's not true, it will just skip and go on to the next one. So let's write in the other one. So if digit count equals 1, and then the next one we'll just do, I'm just going to do a cut and paste here for the last 2, and if digit count is 3, and if digit count is 4. Now we know we're going to do something in here, but we won't get to that in a minute here. I got to do something with digit count down here. So we have to increment digit count. So we'll just do this. Digit count equals digit count plus 1. So that's, we've incremented now, we've added 1 to it. But what happens when digit count gets to 3? And we'll increment it. It's going to hit 4. And do we want it to get to 4? No, because we don't. Oops, I've written this down incorrectly. This should be 2, and then it should be 3. 0, 1, 2, 3 is the range that digit count counts through. So when we increment it each time, digit count, if it happens to be 3 this time, it's going to get incremented to 4. Now we don't want it to go through again, because none of these statements are going to execute because it doesn't equal any of these values. And digit count will get incremented, it'll go to 5, and it'll run through all these again, nothing will happen, it'll get incremented to 6, yada yada yada, forever and ever until it reaches 255, because remember digit count is a byte, and it can take a value of anywhere between 0 and 255. What happens to it at 255 when you increment it? It does what they call rollover. It just becomes 0 again and starts counting. So what will happen is you'll get the display will be updated for the first 4 counts, and then for the next 251 counts, nothing's going to happen. Probably just the last display will be on, the last digit will be on. And it's going to look kind of weird. So what we need to do here is we've got to check this digit count each time we count it and make sure it doesn't go past 4 or even past 3. So let's do that. So we'll do another if statement again. If digit count equals 4, and actually, you know, we could make it, we'll make it equal to 4 because we know it's going to reach 4. If it's equal to 4, then we'll execute this statement here, which will be make it 0 again. So digit count equals, or is assigned the value of 0. So all that does is when it reaches 4, it gets reset back to 0. So all of this stuff up here, every time through this loop, it never sees anything bigger than 3. And that's important because you'll end up with some really strange display, or really strange results if this happens. Now, what we need to do inside each one of these is we've got to turn off, remember in our, I think I wrote that down in our description of the software. Yes, we did. So we got to turn off the current digit that's on. So we know that when we've got to digit count equal to 0, digit 3 was turned on. So we need to turn off digit 3. So how do we do that? It's digital write again. And what pin is digit 3? So 8, 9, 10, it's pin 11. And we want it to go high. Get this right here. So we've turned off that digit. And what we want to do now is we need to convert the value that's in digit 0, which is a number between 0 and 9. We have to convert it into the funny different segment drivers, the 8 different segment drivers, or the 7 different segment drivers that make up the digit. And we'll use a function that we're going to write. We'll call it convert digit. Call it convert digit, and it's going to take a parameter, and we'll call it display digit 0. We haven't defined that or declared that function yet, but we will down below. As a matter of fact, we can do it right now, and that way we can compile this and test it, and the compiler won't complain. So let's quickly define this function, convert digit. So remember how to define a function. You have to declare the return value. In this case, there is going to be a return value, and it needs to be, or no, it's not a return value. Sorry, it doesn't. This function just does something. It doesn't return any value. So we write void and convert digit, but it does take a parameter. And that parameter, it's a value or a variable, and its type is byte. And we can give it any kind of name we want here. Let's just call it C for character or whatever. It doesn't. This name here doesn't have to match what you put in here in the name. It only has to match in the type. So C or A or B or any name you choose will be just fine. Again, there's the curly brackets, and that declares the function. We'll write this one in a minute here. Let's continue on writing this stuff. So now we've convert digit is going to output the 7 bits to that port that controls, or to the I/O pins that controls the segment drivers. And then once we've done that, then we can turn that driver on. Or for the current digit, we can turn the driver for the current digit on. So again, we use digital write and that pin is number 8, and we make it low. And that's all we need to write for this one. And it's going to be the same for each one of these here. So let's just do some cutting and pasting again. We'll put it in here. Now these are going to be different, the digital writes here. So we're going to have to turn, now when we get to this one here, this digit is turned on, so we need to turn it off. So we'll put an 8 in here. And down here we will turn on the current digit, which is 9. And then if we put the same stuff in here, and we want to turn off 9 and turn on 10. And last, this one. We're going to turn off 10 and turn on and turn on 11. And there, very simple, just as we wrote it in our design of the software. Now that's good for now. Let's save this, and then I'm going to put in a couple of comments. So this is the units. No, this is the tenths of volts. And then comment here, we could say turn off previous digit. And set up segments. How about LED segments? And then here we can put in turn on the new digit. And this one here is the, actually this is the tenths of digits of volts, and this one is the hundredths, not the tenths. And so on and so on. I'll fill those in later, the rest of the comments, but it's a good thing to put in the comments, like I keep saying. Now we have a couple of unique digits here. So the decimal point we want to turn on. So the decimal point is carried by this digit here. So we want to turn on the decimal point for this digit, and we know that that's on pin 7. So we need to make it low. Oops. So pin 7, low. And this one's unique, so we'll say turn on the decimal point. And I want to maybe add more comments to this. Something like this is a unique QUE digit. It carries the decimal point. So that's our first unique digit. There's also another one, this one here. Hang on, did I do this right? I put these in the wrong place. Well, let's move this down to here, and this comment goes down here as well. This is the units digit. And then the last one down here is the tens of volts digit. Now it too, this tens of volts digit, has a unique characteristic. I'm going to blank it. I'm going to make sure it's not on if the value of that digit is less than 1. When it's 0, we don't want it to be turned on. So the first thing we need to do is, of course, turn off the previous digit. But here we're going to do something. We're going to do an if statement again. If display digit 3 equals 0, and what will we do in here? We want to blank it. So thinking ahead about this convert digit function, if we give it a value that's not 0 through 9, make it 10, we can catch that and then make sure that none of the segments are turned on. So we'll do this of some value, say 10, and that makes sure the digit is blank. Otherwise, now we'll do an else here. If this statement is true, then execute this instruction. We'll put an else in here. If it's not true, we will execute this instruction, which is going to be just display the digit normally, which I've already written here, but I just put it in the wrong place. And then again, at the end of it, we turn on the digit. So that about covers everything on how to display the digits one after another, because remember, loop runs continuously. All of these instructions between this curly bracket and this one down here get executed over and over again as fast as the microcontroller can do it. So that's very simple code on how to multiplex your display and how to scan the digits. Alright, let's turn our attention to the convert digit function that we're going to write ourselves. Now, what it needs to do is take the value of whatever display digit we're working with, which is, remember, between 0 and 9, and convert that into the 7-segment driver output to the display to build that digit on the display. And so it'll be kind of like this, bunch of digital write functions with each of the digits and either the digit high or low, or the segment, I should say, each of these pin numbers that define the segments, and some will be high, some will be low, in order to turn on the appropriate segments to make the digit. So it'll look something like this. I've got it in another program here. Let's just copy and paste here. And I'll put it into the function here. So that's the first digit. Now I've got an if statement here. So it looks at this character that's passed into the convert digit function to see what value it is. Is it between 0 or it's going to be between 0 and 9. So we have to look at it one at a time. Is it a 0? Is it a 1? Is it a 2? Etc. etc. So if it's a 0, then we turn on and off the segments in order to make the digit appear on the display. So if you remember from my previous tutorial on LEDs, I talked about how a digit is made up of 7 segments. You've got all the segments around the outside plus one in the middle, and they're labeled. The one across the top is A, the 2 down the side are B and C, the one across the bottom is D, and the 2 up the other side are E and F, and the horizontal one in the middle is G. So to make a 0, for example, all of the outside segments are turned on and the middle one is turned off. So that's what I've done here. Segment G is on pin 6, segment A, B, C, D, and F are on these pins here, and we make them all low to turn them on and high to turn this one off. And this pin 7 is the decimal point, and we don't want it turned on as well. So that's what a 0 would look like. Now I sat down and wrote all this out for each of the digits and figured out which segments had to be turned on and which segments had to be turned off, and wrote the appropriate digital write function. So let's go back and we'll do a big copy and paste for the rest of these functions here. And there we go. So each one, if the digit passed to this function is equal to 0, do all this, and then skip all the rest of them. If it's a 1, do this one. If it's 2, etc., etc., all the way down to 9, which is right there. And then I've added an extra one, 10. It's our unique one, or our special case, and it's our blank digit. And I've just turned them all off. Now, there's no checking here if you give it a number greater than 10. It won't know what to do with 11. Nothing's going to happen. The segment drivers are going to be just the same as they were previously. You could try to write a catch-all statement here at the end so that it would catch that case, but you probably don't have to worry too much about it here. Also notice in every case I turn off the decimal point. We don't want the decimal point displayed for most of the time. There's only the one special case, which is taken care of up here where we blank it. So if the tens of volts digit is a 0, then we output the blank right there. If it's not a 0, then we output the digit. So what more can we say about this? What'll happen here is if C is not equal to 0, then it'll drop through. It won't execute any of this. It'll do this test here, and if it's not 1, it'll drop through and not executing any of this. It'll test for 2, etc., etc., and then eventually where it hits the one that actually the digit is, like 5 for example, it'll execute all of these, but it'll continue doing these tests and skipping all of this code all the way through. So that's how this function works. It's not a very elegant way of writing it, but this gets the job done. So that's, let's see, we should probably put a comment here for this function. Converts a digit or a value from 0 to 9 into the segments to display the digit, something like that, whatever makes sense to you. And so there you have it. This is a very quick and dirty way of writing the code. Let's check it, see if there's any errors here. I got a feeling there might be a couple. Well, so far it's going. And it is compiled. I don't think it's going to make it all the way through without errors. Great. So we can write or compile this and then download it into our Arduino, and it should run it just the way I'd shown you previously. As I said, this is a very quick and dirty way of writing this software. I'm going to tell you right off the bat here that this is not the best way to do it. It gets the job done, but there are better ways of writing this. And what I will do is a follow-up tutorial on this and show you how to rewrite this software to make it a lot more readable. There'll be more comments in it probably. These numbers that appear here, I call them magic numbers. They don't mean anything to you, so you went back to this 10 months later, you wouldn't know what those numbers mean. So I'm going to show you a way to replace these with words that make sense to you, but that's another tutorial. So that's it for the software. Like I said, quick and dirty, gets the job done, and it'll work.
Well, there you have it. A simple digital voltmeter. If you've been following along this series of tutorials, I presented a lot of information about interfacing to a microcontroller using the Arduino as the example. So we talked about how an I/O pin, a digital I/O pin, actually works. We talked about the limitations of loading it and drawing more current out of it. We learned how to connect an LED to it with a series resistor, current limiting resistor. We learned how to calculate that value of that resistor. We learned how to use a transistor to drive more current than what the I/O pin can actually handle, and learned how to do the calculations for figuring out the base resistor and the other characteristics, simple characteristics of the transistor. And we learned about multiplexing, using the same I/O pins to do different things. And in this case, using the same I/O pins to drive 4 different digits out of the microcontroller, instead of using separate pins for each digit. We use the same pins over and over again. And then I went into some very basic software and how to write some C language software for making this thing actually work. Oh, and another thing we did was talked about the analog to digital converter and some basic ideas of how it worked as well. And what came out of this was a nice little project that you can make yourself and enhance it, and could make yourself a useful digital voltmeter. Put it into a nice box and hook it up to a display like I did, or up to a power supply like I did here, or to some other project that needs a voltmeter on it. So that's the end of this series of tutorials. I'm going to continue on with some more tutorials on software. Stay tuned for those. But I hope you guys got something out of this. If you enjoyed this, give me a thumbs up and subscribe to the channel, and give me some comments too. I'd like some feedback. I haven't done this before, so I'd like to know how well or how poorly I'm doing on this. So I hope you enjoyed this, and stick around for the next ones. Thanks for watching. Bye.